Newton's method.
As you already know, Sir Isaac Newton was one of the developers of calculus, and he used calculus to help find the roots of a function, that is the zeros, using a linearization method that we now call Newton's method. So Newton's method, what is it? Well, it's a way to find the solutions to the equation f of x equals 0. Sometimes equations get very, very complex. They're very difficult to find the zeros or the roots of a function. So Newton's method is a way, in an iterative fashion, in other words, we have to repeat the process to find that zero. Well, how does it work? Well, what we're going to do is you're going to draw tangent lines from the most recent x value that you have, starting from an initial guess of the zero, and those tangent lines will project out and get you closer and closer x's to finding that zero. Okay, before we get too far into this, here's the joke of the day: how to catch a lion. Now, sometimes it's going to take several iterations to get close enough to the solution for it to be meaningful, and there are times that the solution, the zero, does not even converge at all. The estimations get successfully farther from the zero. So there are occasions where Newton's method fails. So let's get under the hood and figure out how it works. Now, it is a linearization method, so if you haven't seen the linearization screencast, you need to go back and look at that, because we developed an equation for linearizing something by taking the y value that we know and projecting out a tangent line to a point we don't know to find a future point. Well, Newton's method is going to start with this, but it's the x's that we're interested in now. It's finding the x value that gives us a y value of 0. So we're interested in what's happening when f of x1 is equal to 0. And what's the x value that gives that to me? So we put in a 0 for f of x1, and then we solve that equation. Try to solve it for x1. First thing we're going to do is go ahead and move this f of x0 to the left-hand side by subtracting. Trying to isolate x1. Solve this equation for x1. So the next thing we're going to do is we're going to divide both sides by f prime of x0. When we do that, we're almost there to isolating x1. We get f of x0 over f prime of x0, notice the negative sign, equals x1 minus x0. Last thing to do is add x0 to both sides. And when we do that, we get that x1 equals x0 minus f of x0 over f prime of x0. So let's give some meaning to each of these terms. What we're doing with Newton's method is we're starting at an old x value, something that's a guess for the 0. And we're adjusting that by linearizing f of x0 over f prime of x0. Notice there's a negative sign, so it kind of goes backwards. And that value that we get is going to be equal to the new, hopefully closer to 0 value. We're going to call that x1. And we're going to repeat this process until we get an x1 that's as close to 0 as we need it to be. Now, if the process is working, this is going to iterate. We're going to repeat this process, and we're going to get closer and closer to 0. And again, there are some times when it's not going to work, particularly if the derivative is 0 at the point that you pick, or if you wind up getting a point where the derivative is 0, it's going to blow up. But if that doesn't happen, it will converge and give you a good answer. Now, you could probably look at this and see it's pretty tedious. It's a perfect application for computers to do the heavy lifting. In fact, in our class, we're going to try and write a program that's going to do that for you. So let's go ahead and test this out. So we're going to take this function f of x equals 1/2 x to the third minus 4x squared plus 3, which is actually algebraically pretty difficult to find the zeros for. Okay, so we're going to try and find the zeros of this particular function, and we can see that the zero of this function is pretty close to 1. It's very difficult to solve this algebraically, by the way. So we're going to use Newton's method to converge on this 0. We're going to start with an initial guess of x0 equals 0.5. When we plug that into the function, we get f of x0 is approximately 2.0625. Now, since f prime is also, the derivative is also in this formula, we need to compute that for this function as well. Using the power rule, the derivative is equal to 3/2 x squared minus 8x. So Newton's method we're going to take x0 of 0.5, we're going to take f of x0, which is 2.0625, and we're going to evaluate the derivative at x0. And the derivative at 0.5, when you substitute 0.5 for x, is negative 3.625. So when we plug those numbers for x0, f of x0, and f prime of x0 into our equation, we get 0.5 minus 2.0625 divided by negative 3.625 is equal to our new x1, which is 1.069. And visually what we've done is created a new tangent line. And you can see here the tangent is negative 3.625. We've projected that down, and we found a new x value that's quite a bit closer to the 0 than our original x value. That new x value is quite a bit closer to 0 than the previous one, but we got to keep going. So this process repeats itself, but now we're going to use 1.0690 becomes the new starting x value, and we're going to repeat the process. So we repeat the process using x1 as our starting point, and we get 1.0690 minus f of x1, which is negative 0.9608, divided by the derivative at 1.0690, and that gives us a new point, x2, which is approximately 0.9286. And we get that by projecting a tangent line from x1, and you can see that visually in blue. And hopefully you can see that it's getting closer and closer to the actual 0 of the function. In fact, it's so close to the 0 at this point, we're going to have to zoom in to look at it. So we can see even after just 2 iterations, in this case, we've gotten very, very close to the actual 0 of this function, perhaps close enough for whatever our application is. And in fact, if you look here, our new point, 0.9286 for x, is only 0.0487, so about 5/100ths of a distance away from 0. One more iteration will probably get this very, very close, and we're going to do one more iteration. In fact, it's probably a good point to tell you that making a table, like I wrote a little program in Excel to do this, but making a table, even if you're doing it manually, is a great way to go, because it organizes your information very nicely. So what I have here is, the original x of 0.5, I computed f of x and f prime of x, and that's enough information to give me the new x, because it's the original x minus f of x divided by f prime of x gives us the new value. That value in the next iteration becomes the old x value that we start with again, and we repeat the process. And you can see even after just 2 iterations, we were very, very close to the 0, only 0.0486 away. But if we repeated the process one more iteration, we're actually, 16 ten-thousandths of the way close to 0, so in the 5th decimal place. And if we wanted to take it even another iteration, then we're almost completely to the 0. And you can see after 6 iterations, it basically becomes the 0 itself. And I really can't even show you more iterations than 2 or 3 here, because it's just so close to the 0 after the 3rd iteration that it's almost impossible to show. So we looked at Newton's method of finding the zeros to complex equations, and this has a lot of uses in so many different applications. We're going to look at a lot more examples in class, including cases where it fails to converge to a solution.